Hello everyone, my name is Kamal Preet and I've been teaching chemistry from the past many years. So, what I've experienced during my teaching years is the lack of knowledge of basics of chemistry in many students. So, I've come up with these videos in which I'll be teaching basics of chemistry in multiple parts so that you are very much in sync with understanding any chapter, whether it's ninth grade, 10th, 11th, or 12th. So, I'll be covering up all the chapters, at least in high school, and later on we'll see if more chapters we can add and some practice questions videos in the future. So, quickly, without wasting time, I'll start with the basics of chemistry, which I call it as a part one. So, I start this basics part from atom. So, we have seen this structure of atom. This is something very called as imaginary structure of atom. Now, nobody has seen atom like this. The form of information about atoms, electrons, or whatever we want to understand about it. So it's in the spectroscopic methods. So we can get the results in the form of waves, we can get in the form of some spectral lines that we'll discuss in the future classes, or any form, but not this. This is some scientist imagination we call. Now, I have a different way of teaching. This is usually you study in atomic structure chapter, like how this is basically your Neil Bohr atomic model. But since we are doing the basics, so we are going to understand it from a different angle. So this atom is having a nucleus in it. So nucleus is a positively charged central core. So we can write this positive charge later because nucleus has two subatomic particles. We call them as protons and we call them as the second one, that is neutrons. So neutrons is given by a symbol N, protons is given by a symbol P. So protons carry positive charge, neutrons carry no charge. So this core of an atom that we can call it, it's a central part. So I also call this as a heart of an atom because this is majorly governing many things inside an atom. And then we have electrons which are revolving in these imaginary pathways, uh, orbits. We have negatively charged electrons over here. This is negative. So orbits or shells. So orbits and shells, like these are two terms for it has the same meaning, slightly different. I would call it. Orbits are basically the first orbit, the second orbit, the third orbit. Like there are multiple orbits or pathways, imaginary pathways inside an atom where electrons are residing. So shells is in the alphabetical order that we say in the form of k element shells. Most of you have already heard about this. Now, moving ahead, now everyone we know has an identity. So, I introduce myself with my name. So, you know your friends with their name, their address, their everything, like which class they are studying. So, similarly, when we talk about this atom, how do we identify what atom, what element we are talking about? So, we have one identity. I call it as an identity, but it's actually atomic number. So it's given by symbol Z. So it is equal to number of protons in an atom. So if I take an example of carbon atomic number is 6. So we say that it has 6 protons inside an atom. And this proton number can be equal to number of electrons in a neutral atom. So this is how we represent. I'll come back to this part again, the representation of an element. So if Z is an atomic number that is equal to number of protons, that number can be equal to number of electrons, and this is what we call as a neutral atom. So carbon has 6 protons as well as 6 electrons. We can take any other element also. We can take a metal in order to understand the next step. Now, what if the proton number and the atomic number is the same, right? And this electron number is not equal to the proton number. Then we call that as an ion. If this is not equal. So, do proton jump out of the nucleus during chemical reactions? No. It's the electrons which participate during chemical reaction. So, if I have a sodium, sodium atomic number is 11. This is how we represent. Like if you have any symbol X, so how do you write the atomic number? You write on the bottom left. This is the part where I've written. Similarly for carbon also. So it has 11 protons and 11 electrons. Now, what if one electron it's going to donate and change into 11 protons, 10 electrons? There's an second story to this also, that is electronic configuration. I'll come back to that part in a couple of minutes. So point over here is that this was a neutral atom, sodium. Now it has lost one electron in order to participate in chemical reactions. Atoms do not lose electrons until unless they are never going to participate in chemical reactions. So always remember, electrons participate in chemical reactions. So the magnitude, if we talk about over here, the 11 protons and 10 electrons, that is not equal. That means its neutrality is very much disturbed. So that's why there is some extra positive charge which appears on the sodium atom over here. If you compare protons and electrons, electrons are one unit negative charge less, proton is one number more. That extra number appears on the atom, and that's why we call it as an ion. So ions are basically what? These are charged atoms. So charged atoms are never electrically neutral. Electrically neutral atoms are never charged. Just remember that. So ions can be of two types. Ions can be cations, and then you have anions. So cations is something called as positively charged ions, and ions carry negative charge. About this we'll discuss in the future videos. Then after that, atomic number one identity is done for an element, for an atom. So if we talk about the next identity, something called as mass number, that is given by a symbol A. So mass number, it is equal to sum of protons and neutrons in it. So we can write in an atom. So A is equal to N plus P. That's a formula. So if we know, I'll come back to sodium again. Sodium atomic number is 11, mass number is 23. So you can write the mass number on the top left or the top right. It's acceptable, both sides. But atomic number must never be written on the right hand side of the symbol. That's a big no. So it's always on the left. So we can calculate, if we know the mass number and the proton number, we can calculate the neutrons. For example, we can take from sodium. Sodium mass is 23, proton number is 11, so that will give us 12 neutrons. So what we need to remember? We need to remember the atomic number of the element, we need to remember mass numbers, we can actually calculate the neutrons out of it. Now, another thing is that this is a mass number which is sum of neutrons and protons. Neutron and proton are going to be whole number inside an atom. Now, if you have seen a periodic table, I'm sure many of you you might be aware of periodic table. So in that, the elements are having some weights in decimals, like hydrogen is 1.008 and its atomic number is 1. So what is this? How decimal can come over here? That is the atomic weight of the average isotopes of different of not different of isotopes of hydrogen. So that's a different story. That's totally different number. How do we calculate it? We'll definitely discuss, but not in today's lecture. Now, then after that, now mass number, second identity is done. So remember any element X. So how do we represent? The atomic number at the bottom, mass number at the top. Or you can write like this. This is acceptable, but do not write like this, Z on the right hand side, no, big no. So coming to the next part, usually how do we calculate the mass? We calculate we express this mass in AMU values. So 1 AMU, that is your atomic mass unit. Now, this is a very important value, specifically in atomic structure chapter. It is quite, you can say, useful, and if we can memorize it, then why not? So, one atomic mass unit, just like if we are calculating weight in grams, so atomic mass unit is going to help us understand in what units we are calculating the weight of an atom. So 1 AMU, that is roughly equal to 1.66 into 10 raised to the power minus 24 gram. So if we know the actual weight of an atom, so actual weight of any atom in grams, so if we divide it, you can say by if we try to calculate with this this, if we divide them both, so ultimately we will get values in AMU. Like carbon, if you're going to write in the AMU values, it is approximately equal to 12. I'm not writing the decimals. So technically the mass number that you're taking, 12, once you convert them into AMU values, it's approximately equal to the same number that you were having initially. So if I have an atom, one atom weight is some value, then we convert them into AMU, so it's going to be approximately the same number, what mass number we just figured it out over here. So that is what we call as atomic mass unit, or atomic mass we call it. We never call it as a mass number. Mass number is a whole number. Then after that, remember these three values, which are quite useful again. Again, there are multiple ways to calculate it. Mass of one proton. Then I'm writing in kilograms over here, mass of one neutron. And the third value that we are going to write over here is mass of one electron. So mass of one proton is approximately 1.6275 into 10 raised to the power minus 27 kilogram. Now this value in different books will be slightly different, but I can say 1.6 is definitely there into 10 raised to the power minus 27. And then neutron is 1.6725 into 10 raised to the power minus 27 kilogram. So if we see this value, it proves that neutrons are slightly heavier than protons. Then electron is negligible mass, we say, that is 9.1 into 10 to the power minus 31 kg. So from these values, again there are ways to calculate this. About that historical part, we'll figure it out later. Main thing is the application. Now if I have a chapter, if I have any chemistry chapter, I don't know the basics that this value is very much important to remember, then what's the use? So if there is a there is a you can say pathway, there is a you can say a guideline that yes, this is how you need to study, these are the things that we need to remember, and without this chemistry will be very much difficult in our brain, so we have to make it easy. So if you study any other subject, maths, you need to remember you need to remember multiple formulas. So in order to study any subject, you have to remember something. So based on these values, I can say neutrons are slightly heavier than protons and electrons carry negligible mass. Now, there are many twists and turns in chemistry as you go from 9th to 10th, 10th to 11th, 11th and 12th, or you go to college, you study organic, inorganic, physical. So, there are multiple twists and turns at every stage, every year. So, we should always keep an open mind in our wherever we study, so that we can accept those exceptions, we can accept that these twists and turns can happen, and every element in the periodic table is different, even if some of them have a similarity. So after this, I'll be going to the next part, that is electronic configuration. Now this is again a part of Bohr atomic model, Niels Bohr atomic model. So electronic configuration is nothing but representation or arrangement of electrons in the respective shells or orbits. So now we have shells inside an atom. I'm going to draw this again. Nucleus, the shell, first shell, the second, third. I'm going to draw only three for now. So the very first, which is nearest to the nucleus, is something we call it as K shell. Then we have L, then we have M. So similarly, we have N and so on. So K is the first orbit, K shell, and this is given by the scientist named Cossel Lewis. This is our second, third, Maxwell, and then N stand for Niels Bohr. After that, whatever shell name that we're going to introduce, like these are the more famous four KLMN scientist name. Then after that, the orbit number, the fourth, like that works. Now, one more terminology which is very much important over here is the term something called as valence shell. So I'm considering over here inside an atom that this third shell is a valence shell. Every atom will have a different valence shell depending upon the number of electrons. That we'll just understand in a minute. So valence shell is the shell, or simply we can write outermost shell. So if we have two shells, the outermost shell is going to be second. If we have four shells, the outermost shell is going to be fourth, like that. So valence is the term outermost. Then the second last shell. Now this is what we call as last shell of an atom, whatever, for a particular atom. Then the second last shell is called as penultimate shell. That's a name because electrons usually participate in chemical reactions from the valence shell. Usually. But it's not always the case. Sometimes electrons jump from the penultimate shell also. That is the second last shell. Then if you go to the third last shell, third last shell is something called as anti-penultimate shell. So That can also be possible, that electrons moving from participating in the chemical reaction from the third last shell. Now that is way too ahead we are talking, but it can happen. Keep an open mind. But what is important over here is the terms: penultimate shell, anti-penultimate shell, then we have valence shell. This is very much important. Now, in order to understand these shells, like what are these, we need to understand another rule that is called as Bober-Bury rule, or scheme also we call it. That is given as 2 whole n square. See, inside an atom, just imagine, how do we know what are electrons? How do we know that what are protons, neutrons? So the scientists named it. So how do we know in which country you're sitting? How do we know that? Somebody named it. So that's a place where you are. So these shells names are governed with the presence of electrons. So where electrons are, so how they're moving, in what path they're moving. So we are just naming that pathway. So we are applying maths, geometry to the structure of atom in order to understand the behavior of electrons over here. So now we are going to understand in these areas that we have termed K, L, M, and shells, first, second, third, fourth orbit, and so on. How we are going to arrange the electrons, or how electrons are going to arrange themselves. So based on the space provided. So 2 whole n square, n is nothing but the number of orbit. So if I put one value, that means the first orbit value, it will give us 2 electrons. So Bohr-Bury scheme indicates about the capacity of shells or orbits for holding electrons. I always write electrons as E minus. So this is our K shell holding only 2 electrons. Now it totally depends upon the space. So K shell, that shell very near to the nucleus, the very first shell in near to the nucleus, has a capacity of holding only 2 electrons. So if we want to forcefully add the third electron over there, because of electronic repulsions, it will jump to the next shell. So this, if we do it, 2 into 2, 4 into 2, 8 electrons, that's a maximum capacity. So we are talking about over here maximum capacity of shells or orbits. So K can accommodate only 2 electrons. The third electron will automatically jump into the L shell. L can accommodate 8 electrons maximum. The ninth will go into the third orbit. That is 18 electrons. So this is M shell. So what we need to remember over here, these capacities are based on some repulsive forces, and the repulsive forces are between electrons. Do remember, at the end of the day, electrons are negatively charged. They will repel each other. They can have minimum repulsions, but if we forcefully put them together, they will repel and they will move farther away from each other because same charges will repel. Then if we go to the fourth, this is 32 electrons, n shell, and so on. We can keep on calculating for the fifth orbit, sixth orbit, seventh orbit, and so on. Now, this only indicates about the maximum capacity of shells for holding electrons. It doesn't indicate about the stability of any atom and how electrons are going to be distributed, how they are going to be, like, sometimes they don't follow properly over here, like in the M shell. Sometimes we get 8 electrons. So why is that? So it's because of some other stable gases by nature, we call them as noble gases. So I'll stop over here for for this lecture. I'll be continuing from here with the noble gases, octet rule, duplet rule, and the electronic configuration of 1 to 20 in the next class. Meantime, this whole thing, you can at least give it some time, half an hour, or maybe 25 or 15 minutes time to memorize all this, so that it's easier for you to understand the next lecture. So, thank you for learning with me. This is Kamal Preet. I'll see you soon in the next video.